Yeah, I think we can start now. So good afternoon, everyone. Welcome to MBZUAI's webinar. Today, we are very happy to have Professor Law Song with us. He is the Deputy Chair of the Machine Learning Department at MBZUAI. Prior to joining MBZUAI, he was an Associate Professor in the College of Computing at Georgia Institute of Technology. And even before that, he has worked as a research scientist at Google, and he also did his postdoc at Carnegie Mellon University. Prof. La Song's principal research area is in machine learning, especially kernel methods, deep learning, and probabilistic graphical models. He is a recipient of many desk paper awards at major machine learning conferences, including NeurIPS, ICML, and EASTATS. And he has also won the NSF Career Award. He has also served as the area chair for many leading machine learning and AI conferences such as NeurIPS, ICML, ICLR, AAAI, IJCAI, and he's also the action editor for top journals such as JMLR and IEEE PAMI. He's also a board member at the International Conference for Machine Learning. Today, the title of his talk is on graph neural networks for representation learning and symbolic reasoning. So with this, I'll hand over the floor to Professor La Song for his presentation.
Okay, thanks, Kasi, for the introduction. So today I'm going to talk about learning over graphs, and especially I'm going to introduce to you these lines of work I've been doing in the past few years on using something called graph neural nets for learning representation for these graphs and using that to perform reasoning. So why graph is important? If you look at different type of applications, it doesn't matter whether you work on social network, on knowledge graph, or working on something like information sharing networks such as Twitter and other things, you will invariably encounter networks. So other applications such as transportation network in smart city and molecular graph supporting interaction network in healthcare related problems, you will invariably see graph structures. So in this case, in the molecular case, you can imagine each one is actin in the molecule is a node. And then each one of these chemical bond is going to be edge. It's actually a small graph corresponding to each one of this molecule. So, and another graph you encounter in smart city is the electrical network. In all these problems, in some sense, you have some graph structure connecting the nodes. And then the nodes can be different types, or the edge can be different types. So one central question when you're trying to learn from this graph structure is, how do you actually represent these node in the graph as some kind of vector? For instance, if you want to predict the property of the node in the graph, and then you will need to think about some features. So many machine learning algorithms relies on a set of feature inputs in order to build this predictive model. For instance, if you have a graph, maybe you want to build a predictive model for the node, whether it's a fraudulent node or not. So traditionally, then machine learning algorithm engineers will think very hard about the features. For instance, he's going to look at the location of the person and the age of the person, maybe what kind of neighbor this person has, and whether he has some record of buying something, to come up with some feature vector before he can make a prediction about whether this is a fraudulent account or not, or make a prediction of how many loans I should approve for this particular person. So there are many applications, including recommendation, forecasting of spread of information, and maybe even classification of the interaction between people and probably a node will require some kind of a representation or feature designed from the graph. So graph is quite different from other data types such as images, right? The images, you will actually obtain a matrix of inputs, and then each pixel you will have some kind of real valued numbers, and it's quite regular in some sense. Graph is less regular because the number of nodes can vary across different graphs, and then the connectivity is also going to be sparse, and it's quite irregular. So the question is, the central question here is, how do you actually learn some kind of vector representation before you can pass that into some standard machine learning algorithms? So just to give you a concrete example how these feature design for graphs are being done previously, I would and then the typical designs of this feature vector can lead to actually explosive feature spaces. For instance, there's this problem for designing feature vector for molecules. So in this particular case, there's a data set, public data set out there, which is the Harvard Clean Energy data sets. It contains 2.3 million organic molecules for solar panel materials. So each one of these molecules, depending on how these actins are being composed together to form this molecular graph, it has different efficiency of converting sunlight to energy. So what you want to do is to, given you a new molecule, maybe before you synthesize it, you want to make a prediction about its efficiency of converting sunlight to energy. And you want to actually design this molecule to optimize this efficiency. So these 2.3 million data set are already collected or computed. Each one of these molecule is going to associate with a number between 0 and 12 corresponding to the efficiency of converting sunlight to energy. So in order to build a machine learning model to predict the efficiency of an individual molecule, then you have to design a set of features. So one commonly used type of feature is going to be something called structure, bag of structures. It's similar to bag of words in natural language processing. Here, you're using a small set of, actually a large collection of structures, small structures. For instance, you might look at some structure right here, where you have a center node, which is a blue actin, and then connected to two gray actin. This blue actin may corresponding to nitrogen, for instance. Okay, it connects to two carbon. And then you might also look at some pattern where you have a center yellow actin and connecting to two gray actins. You might even look at an even more complex substructure such as this, containing multiple red nodes. And then you will actually count the number of occurrences of these substructure in particular kind of a graph, and then use these counts as some kind of features. So because this graph structure and the corresponding subgraph containing this particular graph is a combinatorial optimized object. And then depending on the type of actin you're putting into it and the connectivity, the number of possible substructure can actually grow exponentially. So actually for this 2.3 million organic molecule data sets, if you want to actually use this type of background structure feature to obtain a good enough prediction, so you actually need to go to 1 billion dimensional features. Of course, each individual molecule is going to get obtain a sparse representation, but you indeed need 1 billion features in order to do that. That means that the subsequent machine learning model built upon this 1 billion feature may actually have lots of parameters, right? The input dimension 1 billion, and you will have lots of parameters. Okay, and then what's graph neural net? Yeah, graph neural net is a way to actually learn feature representation from graphs. And then this slide is going to give you a summary or the introduction, very quick introduction about graph neural nets. So it has many variations already, but the basic version is something like this. So you will have a graph. In this particular case, H1 to H6, they are the nodes in the graph. And it can be a person in a particular, football club, for instance. And then associated with each one is node, there may be some additional features, such as an image describing the player, football player. And then it might be, the feature may be a chunk of text describing some information about the particular person. And then this graph neural net will try to learn a vector representation for each node in this graph. And it's going to initialized with this feature on the node and applying some kind of neural network parameter W1 to reduce it to the initial embedding, a vector of a fixed dimension. For instance, here is a 3-dimensional vector. Afterwards, you are going to update this feature iteratively using some kind of message passing operator parameterized by graph neural nets. So in order to update this vector embedding, you will request the neighbor of this node to send their current embedding to the center node. Okay, you will request the neighbor to sending their current representation, perform some kind of pooling operation for these neighboring embeddings, and afterwards you perform additional transformation before you send out this message or before you update the embedding for a particular node. So these embedding update step, message passing and embedding update step is going to carry out for each node in parallel. And once you finish 1 round of update, you're going to carry out the second round. You're going to do T round when you are doing T-rounds of this message passing operation, you can imagine that the information from neighbors from T hops away, they will also be propagate into this particular node. And this embedding vector, which is finite dimension, is going to integrate information from neighbors, not just the node feature for that particular node, but also some connectivity information and even the information from the feature or node feature from the neighboring node as well. Okay. And then the key thing in graph neural net is this message passing operator is not going to be fixed beforehand, but it's going to be parameterized by some neural nets. And the primary W1, W2 here is going to also be learned with using some kind of subsequent supervision signal, some kind of subsequent loss function. So you can imagine after I finish T rounds of message passing operation, each one is node in the graph neural net. Each node in this graph is going to have some kind of vector representation. At this point, and then I can use this vector representation to define some of the learning objective or learning task. For instance, if I want to predict the property of a node, I would just take the embedding of a particular node and build a classifier for it. If I want to actually predict interaction between the node, I'm going to take a pair of nodes and then look at the embedding, define some kind of classification model out of it. Okay, so sometimes if this entire graph is going to be a molecule, I actually want to make a prediction about the property of the entire molecule. Then I will actually take the embedding for each one is node and perform some pooling operation before I build the classifier. So I've been talking about using classification objective function to learn this parameter in this graph neural net. But you can actually also combine graph neural net with many other downstream tasks, such as generative model and then reinforcement learning. You will see some of these examples in the later part of the talk. So just to give you a concrete example, how this graph neural net can help learning a very compact representation from the graph, I will just come back to this example I mentioned earlier for this organic molecule prediction, probability prediction problem. So you can think about in this case, each one is a molecule, is going to correspond to the graph, it's going to be one input data point. And each one is data point is going to associate it with some number, real number between 0 and 12. It's a regression problem. So you will use graph neural nets and run graph neural net on top of this graph structure. You will obtain a set of vector representation for each one is node. And then you can perform some kind of average pooling of these embeddings to obtain some kind of representation or feature representation for the entire molecule. And then once you have this feature representation, you will have for a regression model. In this case, you have additional set of parameter V, which links this embedding representation of the molecule to the regression target. Then you can set up some kind of least square objective function to try to optimize the parameter in this regression model, and also those parameters in this graph neural net, which helps you to perform and integrate structure information in the message passing process. Once you actually learn this graph neural net for feature extraction and property prediction in this molecular data set, you will find that it's actually learning some very compact representation and also allows you to achieve state-of-the-art prediction for this property. So here is a comparison between the representation learned by graph neural net and some of the traditional way of representing graph structure. So this traditional way called Weisfeiler-Lehmann feature or Weisfeiler-Lehmann kernel, it's designed from the kernel community. It's trying to describe the graph using a bag of substructure type of representation. So here, what I'm showing in the horizontal axis are the dimension of the feature, right? If you use this Weisfeiler-Lehmann feature and go to 1 billion dimensional feature space, you're able to actually build a model which gives you a mean square error, mean average, mean absolute error of 0.95 with such a high dimensional feature space. If you reduce the feature space or compress the feature space by 10 times, then your performance will drop and the error will go up. And as you compress this representation, this hand design feature by 1,000 times, then your MAE becomes 0.28. It's much worse than this 1 billion dimensional feature space. And graph neural net is able to learn with a feature space just a few hundred dimensions, yeah, and being able to achieve the state-of-art model for making prediction about the property of this molecule, right? And graph neural net in some sense is able to achieve comparable or even better predictive results with a much smaller feature representation model sizes. So this is some powerful kind of a property you can obtain using this graph neural net. It learns a set of useful features for making the prediction for these molecular data sets instead of starting from a set of possible useful features and learn and then let the algorithm to chain down to some useful set. Okay. So this is a one application where you actually take the entire graph and trying to actually make a prediction about the property of the entire graph. So there's another application which is more on a social and bigger scale network scenario, is this fraudulent account detection problem. I've worked with Alibaba previously on an online payment platform problem. You try to detect whether a particular online payment account is a fraudulent account or not. So in this particular case, there are two types of nodes. It's not just one type of node. There's some type of node which is corresponding to the account, and there's also one type of node which is a device. If that particular account has ever logged into that device, you'll have an edge connecting them. So you can imagine that there may be multiple accounts connecting to the same device because you use the same device for login. And then one account can log into multiple devices. Well, besides that, each individual account has its activity kind of information, right? So the question is actually whether you can integrate these two sorts of information, connectivity information and the account level information. Both actually contain some information about whether this particular account is fraudulent or not. So here, just a quick look at the data. You will see both type of information is actually useful for this fraudulent account detection. So what I'm showing on the left column is going to be the behavior of normal accounts. And then the horizontal axis is going to plot in the device ID. And then the vertical axis is account ID. If that particular account has ever logged into a particular device, then it has some as a dot here, right? The data has been sorted such that it looks like there's some, stripes here, but it's most of the normal accounts, they log into random, device number. You can think about this. And then for the normal account, you can also look at the time from the registration account and the activity after that point. So essentially what is showing here is the time, and the horizontal vertical axis is the account ID. So for the particular account, when it is registered, then you will actually see this kind of periodic kind of behavior of the account. Maybe during the weekend, you have more payments, and then during the weekend, you have less things like this, or maybe the other one around. During the weekday, you have more payments, and after some particular points, you have less payment. You have this periodic behavior, and the beginning, you have more kind of payment behavior. But if you look at the right column, the foreign account, in terms of the connectivity between the account ID and device ID, it looks very different from the patterns for the normal accounts. So there's much clearer kind of vertical lines appearing in the foreign account case. In this particular case, actually that means that for fraudulent account, some device tend to have more account logged into it. So it's just because some of these devices are expensive to get, right? And then the fraudulent people may actually create multiple accounts and just using a single device login. And then for the activity, you can see there much less activity for fraudulent account. So in both dimensions, in terms of the network connectivity and also the activity of the node itself, there's information about the fraudulent behavior. So graph neural net is able to integrate this source of information to come up with a better feature for prediction. For instance, if you use graph neural net to build a fraudulent account detection model, it will lead to quite a big improvements in terms of this precision recall curve. In this case, you want the precision recall curve to be as high as possible. And then graph neural net-based approach is able to achieve a very high precision recall curve. And the previous approach based on human designed rules or some unsupervised learning of these graph feature actually perform much worse in this case. Okay, so so you have now seen a quick introduction about graph neural nets. And also you've seen two applications, one in molecular graph property prediction, the other one in fraudulent account detection. I'm going to go a little bit deeper and explain a little bit on how to understand this graph neural net representation. What kind of features being learned? Can we make analogy to some of the traditional way of designing graph features and to see the benefit or advantage of graph neural net? To do that, I'm going to actually refer back to a very traditional algorithm for graph isomorphism test. This algorithm is called the Weisfeiler-Lehmann graph isomorphism test. And for instance, here is the problem where you have two graphs, x and x pi. And the question is whether they are the same or not. So the number on the nodes are going to be the type of the node. So you might have different type in a more complex graph, but in this particular simple example, all the nodes have the same type. So its node has type 1. And what's differentiating between these two graphs are really just a connectivity pattern. So you want to actually design an algorithm such that you can separate, you can tell or test whether these two graphs are the same or not based on the connectivity pattern. So one famous algorithm in this space is called the Weisfeiler-Lehmann test. So this algorithm is going to run in an iterative fashion and also in a message passive fashion. So in this case, each node will actually ask its neighbor to pass in the messages. And in this particular case, the message is just going to be the type of the node. For instance, the node here on the upper left corner is going to have 3 neighbors of 1s. You ask the neighbor to pass in the messages, and you're going to store these neighbors type as some kind of a suffix. So this representation here in the bottom graph, where you have 1 at the beginning with a comma and 111 is called multiset representation of these node and this neighborhood. So similarly, you have this top node here, 1 with 2 neighbors. Then it's going to, after message passing, it's going to have a multiset representation like 111. Okay. So every node is going to perform this message passing and record the neighbor's node type. In the similar fashion, you obtain a graph, 2 graphs in the bottom here. So at this point, you can actually simplify the node type. You can map this multiset label to some simpler kind of node label. So in this particular case, I will just design a mapping where 111 is going to map to 2, the type 2 node. 1 with the 3 neighbors of 1s is going to map to type 3. And this one with the 4 1s in the suffix is going to be mapped to type 4. So you can simplify this multiset label representation to something like this here, okay? So you have now node type 2, 3, 4 in the graph, okay? And then what we hope is we can actually tell the graph whether they are different or not by just counting the number of nodes with a particular type. For instance, in this particular case, we have type 2 node, 3 type 2 node in the left graph, and 2 type 3 node in here, and 1 type 4 node. So actually, the number of type 2 node is also 3 in the second graph. Type 3 nodes is 2, type 4 node is also 1. So you cannot tell the difference between these two graphs by just counting the number of nodes with a particular type. So that means that after first iteration, it's not sufficient to differentiate between these two graphs just by counting the number of nodes with a particular type. At this point, then you actually run your message passing iteration for the second time. And each node is again going to be augmented by the node type of its neighbors. For instance, for the top rightmost node here, top leftmost node here, 3, it has a neighbor of 2, 2, and 4. So that's why you have these multi-set label again is 3, comma with 2, 4, 2. Okay, you do this similarly for all other nodes, and then you design a table to simplify these multi-set label again, and creating node type 5, 6, 7, 8, 9, 10, and you get a graph like this on the left, and a graph like this on the right. So then at this point, actually you can easily differentiate between these two graphs just by counting the number of nodes with certain type. So for instance, for the left graph, you will not have node type 5, but in the right graph, you have 2 nodes of type 5. Immediately you can say that these two graphs are different. Okay, so in some sense, you are designing a new feature space for these two graphs, and each feature dimension of these representation is going to correspond to the count of the nodes with a particular type. Okay, you have type 1, 2, 3, 4, 5, up to 10 type node. And for the first graph, it has 6 of type 1, 3 of type 2, and then 2 of type 3, things like this. And then for the second graph, you have 6 type 1 node, and 3 type 2, and 2 type 1, and 1 type 4, and 2 type 5. And then you can think about these feature representation is going to obtain in an iterative fashion, and it's going to summarize the structure information of the node, right? So if these two representations are not the same, you would know that the graph are definitely not the same. Otherwise, it can be the same graph if you just stop in the T level of feature, T iteration. And then they might be the same, or you cannot tell the difference, okay? So actually, what plays a key role in this feature construction is the so-called mapping from this type of multi-set label. Message passing is definitely one important operation. The second important operation is actually the mapping of the multi-set label to a new node, new code. For instance, your mapping is 1, 1, 1 to 2, 1, 1, 1, 1 to 3, right? This is actually just designed by hand, this mapping. So you can actually generalize this mapping to just some neural net function, and then allows it to be parameterized and learned together with this message passing operation. So that's actually going to correspond to graph neural nets. So essentially, this mapping is a mapping from multi-set object to a number. So actually, in order to represent this type of functions, there's some representation theorem saying that the mapping has to take a form like this. First, you apply F to individual incoming messages, and then you do kind of sum pooling, and then you apply the second function to the pooled kind of messages. And that's going to be a general representation for the multi-set function. And graph neural net parameterization is a particular instance of that multi-set function, trying to map this the immediate neighborhood structure into some kind of new code, okay? And based on this representation, understanding and connection to this Weisfeiler-Lehmann kind of graph isomorphism test, one can also show that actually max pooling and min pooling actually they are not as expressive comparing to sum pooling. Sum pooling will be more expressive, because max pooling and min pooling, they cannot differentiate. For instance, the graph on the left here and the right here, they have different structure, but the proportion of green neighbors and red neighbors are the same. By doing this max pooling or min pooling, you actually cannot differentiate these two structures. So you can think about this. The graph neural net is actually the message passing operator is parameterizing some multi-set function. And you try to actually aggregate this type of neighborhood structure into some code, okay? And then that code is going to be our feature representation. And graph neural parameterize that feature function and allow you to learn and compress it to a very small dimensional feature, okay? So people also find that the graph neural net has, when it operates on knowledge graph, has close connection with logic reasoning, okay? So just to give you some mapping between logic formula or logic reasoning to graph structure, I will actually provide a simple example here where you have a very simple formula where you have a predicates, some relationship such as X, Y, the husband, and then Y and Z, Y is Z's mother, and then you can derive that the Z is the daughter of X, right? So if you can actually represent this relational graph as either a factor graph like this, and on the bottom here are the entities, X, Y, Z are the entity or person, and then on the top row are going to the factor node corresponding to these predicate, these relationships. Okay, and similarly, you can actually also represent this logic relationship as a graph like this, where you have three entities X, Y, Z, and then the arrow is pointing to some kind of relationship with some type. Okay, and then if you see a particular graph pattern such as X pointing to Y with a husband relationship, Y points to Z with mother relationship, then you can derive there's an edge present between X and Z with the daughter relationships. So in some sense, based on graph structure, you can make a prediction about whether X and Z has particular relationship if you are able to learn this logic formula on the top here. And you can also predict some of the property of the node. Sometimes the logic formula is actually used to derive some property of some node. So people have also done some theoretical study on these aspects and showing that essentially I'm not going to go into details of this first order logic formula with two variables, and then essentially it's a subset of logic formulas, and you can show that the commutation and function mapping is equivalent to this WL Weisfeiler-Lehmann test and GMN graph neural net with infinite depth. When you have finite GMN, that means you run iteration on graph only for finite number of steps. So this GNN is actually not expressive enough. You actually need to use some kind of readout global pooling in order to obtain some long range information to be able to represent some of this logic formula. Okay. Just to show you a bit how graph neural net can be used to learn some interesting, logical relationship or reasoning, temporal reasoning kind of patterns. I'm going to use this example, this data set to give you a quick example. Here is a data set called the GDELT, and it is created from news articles, and events are extracted actually from these news articles spanning in the past 215 years. And you're going to extract something like subject, maybe it's a country, and relationship, another country, right? And the time of that particular event happened. Maybe something like this country has a war with the other country. This country has a contract with the other country, right? This country had a cooperation with the other country. Okay, at a particular point in time, you can actually feed this graph, historical graph into graph neural nets. Actually, in this case, you need an extension to temporal kind of a graph neural net or dynamic graph neural nets. And you want to use this historical graph connectivity pattern to learn these graph neural nets and make a prediction about the future events, make a prediction about what could happen in future, right? Which two entity is going to form a relationship, what type of relationship it is, and when this particular event is going to happen. This graph neural net is actually able to build a model which are very accurate compared to the past model in terms of predicting this type of future events. I just give you two examples where these graph neural nets are making much more accurate prediction comparing to other models. The first example is this one. So the dashed line here are actually some target events you want to predict. So there's some news during 2015 saying that some people from Croatia are being attacked by people in the Cairo. And graph neural net is actually conditioning on, leveraging the graph structure before these time points. So you see all these solid nodes and edges are even happening before this prediction, such as, you have this threatening relationship, providing aid, and then consulting for help and cooperation type of nodes, right? And then the red edge are generally, you know, adversarial kind of relationship or negative relationship. And the green ones are positive relationships. And based on this graph connectivity pattern for the event happened in the past, for instance, for this particular case, you have a negative relationship between these two nodes and positive relationship between these two nodes. And then it's likely that there's a negative kind of relationship going to happen in future for this. And then similarly, you have another powerful negative relationship and the positive relationship. Together, these two graph structure, it reinforce the fact that there may be some positive, negative kind of relationship happening between these two nodes. And it's going to happen in recent time. So the graph neural net is going to actually is able to learn this type of connectivity pattern and make a good prediction about this. Okay, it seems to summarize some of the folklore kind of behavior in the social network where the enemy's friends is the enemy. Okay. So you can actually look at the more complex kind of graph pattern. In this particular case, it's some kind of cooperation kind of behavior. So first, this node, Colombia, has some collaboration, trade cooperation with New Delhi, some city in India. And then this New Delhi has some diplomatic cooperation with Ottawa, this city. And there's another path in the past where Colombia has reduced the relationship with Belgium. Belgium has some trade fight with Ottawa. And there's a positive path, a negative path. It reinforces this prediction that there may be some positive connection between Colombia and Ottawa. So this pattern is like a folklore rule, such as a friend is a friend. If there's a common enemy, then it strengthens the tie between these two nodes, right? This is a common enemy, like, and then it strengthens tie here and making this relationship more likely to happen and happen in near future. Okay, so this is something you can actually learn with graph neural nets to capture some of the connectivity pattern and graph structure, which allows you to make this type of logic reasoning. Right? So this is the application of graph neural net for logic reasoning. So there's another actually interesting areas of application of graph neural net is using graph neural net to learn new algorithms. For instance, one algorithm many people are familiar with the so-called PageRank algorithm, which is behind Google's search engine. In this particular case, there's a network, maybe a social network, people referring to the other people for information, or it might be web pages. One web page is linking to the other web page for more authoritative information. And then you want to assign a number, a single number scalar to each one of these node in the graph, such that the node with higher number is going to be more authoritative or the more important node. So actually this number can be attained using some iterative algorithm where you start by initializing these numbers, and you're going to update this number by asking the neighbors of this node to pass in messages, and weight these messages are the current ranking of the neighbors. You're going to perform weighted average of these rankings of the neighbors. So essentially, if your neighbor are all important, but they are also referring you for information, then you are becoming even more authoritative. So essentially, after final number iterations, this ranking number is going to converge to something, and you will call that the number is the PageRank of a particular node in the graph. So you can see that this PageRank algorithm is a very simple massive passing algorithm. And it's asking first, it's a one-dimensional representation for each node. It's performing a very simple weighted sum of the neighbors according to the edge weights, WJI. And it doesn't have nonlinear operations, and these particular updates are hand designed. Actually, the PageRank may be useful for coming out with some kind of ranking of the node, but it might not be good for other tasks such as predicting some particular property of the node. So you can think about that the graph neural net is a generalization of this type of massive passing algorithms in the graph. First, it has a more expressive representation for the node. It's a vector instead of a number, right? The second thing is this massive passing operator to aggregate information from a neighbor is not going to be designed by hand or with a fixed parameter, but it's going to be parameterized by some kind of neural nets with the parameter W1, W2. And this message aggregation process in some sense is also going to be learned. And furthermore, with this embedding representation, you're going to use downstream task or objective function to optimize the parameter of these message passing operator, determine what kind of information need to be passed and how do you aggregate information instead of pre-designed a function to aggregate information, a particular type of information. That allows you, that parameterization of this graph neural net allows you to, in some sense, to search over the space of graph algorithms. And you can actually use this graph neural net as a module in designing some kind of algorithm for solving graph problems. So I'm giving you an example here for combinatorial optimization of a graph, where you actually see this type of problem in either social advertisement case. For instance, if Twitter has a network connecting people, you want to select some people to tweet about something such that more people can know about this information. And there's this minimum width cover problem. And maybe it is about immunology. You have this social content network. You want to select a set of people to immunize, such that you can create island in the graph, such that people won't spread the diseases. So you can actually frame many problems into this canonical computer science problem called the minimum width cover problem. So to state it more formally, you're going to, in this particular problem, you're going to attach each one is node with some flag, which is xi, which is either 0 or 1. And you want to select the subset of node to make the flag becoming 1, okay? Selecting node for advertisement or selecting node for immunization. And then you want to make sure the selected node is minimized. That's why you want to minimize the sum of xi. Sum of the node where the flag is 1 is small, okay? The constraint is you know to make sure that each one is edge, each one is a social link. At least one end is being selected, at least one end is advertised or immunized, okay? So it's such a simple problem, and then, but it's an NP-hard problem. And in order to solve it, you will need to check a large set of possible selections. People have come up with some approximation algorithm, which is simple. Just start it greedily, and then you will just select node with high degree, or select an edge where both ends of the edge has high degree. And once you select the node, you're going to delete the incident edges, and then work on the remaining graph. Okay. So this algorithm is very simple, but it's you can show that it's a proof approximation algorithm. That means the objective function will not be will be at most 2 times as large as the global optimum. Okay. So, but this particular algorithm is going to be hand designed, right? It's just using the degree of the node. So in some sense, you just use first order neighbor information, right? And and since graph neural net is able to search over the space of massive passing operator and how you aggregate information from neighbors, the question is, can we actually parameterize these selection criteria using graph neural nets and then learn the graph algorithms based on data? Okay. In order to do that, you actually first frame the problem in the framework of Markov decision process. So this is the optimization problem, and you can actually map the terms in this optimization problem into the language which is typically used in Markov decision process and reinforcement learning. Here you try to select the node. Suppose you are going to select it one by one. So every time you select the node, you're going to actually penalize it. That means your reward is -1, okay? You want to select a small number of nodes as possible. And then your current state of the problem is going to the graph, right? With those nodes and edges which hasn't been selected. And then you have some action value function, which in this case is just a degree of the node given the current graph. And the greedy algorithm is going to just take greedy action based on this action value function and select the node and remove it from the graph. You obtain updated states, and you go back, and then you're going to recompute the action value function and reselect the node using greedily. Okay. So this two approximation algorithm is designed by hand, and you can actually replace essentially the action value function by graph neural nets, and define your action value function using this embedding you obtained from graph neural nets. So you define essentially this action value function with parameter theta1, theta2, theta3 using, and also this embedding obtained from graph neural nets. You're going to actually train or learn the parameter in this action value function together with those parameters in the graph neural net using, for instance, Q-learning, okay? Using this reward function -1. Once you have learned this action value function, then you can actually take a new problem, right? A new graph, and then apply this learned action value function on this new graph to perform the selection of node and solve new problems. So you will find that if you're using this graph neural net to actually learn a graph from a family of problem instances, you will actually obtain an algorithm which is much better comparing to these greedy algorithms. Here I'm giving you some visualization of the algorithm in action. Here are 3 graphs, okay? They are exactly the same. The major difference is created by just the visualization. They're really the same graph. So I'm going to use 3 algorithms to select the nodes to solve the problem. The leftmost one is going to be produced by this learned graph neural net algorithm. And the middle one is going to correspond to selecting node greedily according to node degree. And the rightmost one is going to select the pair of node corresponding to the edge. The sum of the degree of the nodes in 2 end of edge are large. And algorithm is better or faster, then it can actually finish the graph faster. Okay, it can clear out the edge faster. Okay, let's just take a look how these algorithms are in actions. So every time you select some node, you're going to remove it from the graph. You're going to work on the remaining graph. At the beginning, the node greedy and edge greedy seems to be good, right? It actually clear out the edges pretty fast. And then this graph neural net based algorithm seems to still have lots of edge to work on. But near the end of the algorithm, you will find that actually the algorithm based on graph neural nets is able to solve the problem faster compared to greedy, node greedy and edge greedy. So why is this the case? Because we can look at this video again, because actually the node selected by this learned graph neural net algorithm is able to balance a bit between the degree of the node and then the connectivity of the node. By removing this node, you don't want the original graph to be disconnected, such that even near the ends of the algorithm, and there's still a potential to select the node and remove lots of edges. What happened to this node greedy algorithm? An edge greedy algorithm is too greedy, and it doesn't consider long-term kind of effects of selecting the nodes. And it creates a graph which fragment into lots of disconnected components. And then in the end of the algorithm, you're forced to select at least one node for each one of these components in order to solve the problem. But for the one which is produced by graph neural net, it's keeping the graph pretty much connected, such that it actually gets accelerated near the ends of the algorithm. Okay, so this is very interesting. Essentially, using these parameterized graph algorithms and reinforcement learning, you're able to actually discover some new algorithm beyond hand design algorithm, which is actually performing better in these examples. So there's this is just an example which is being used in many world discovery. People have also used this type of graph neural nets and learning-based approach to design algorithm for solving minimum dominant set, maximum max cut problem, and challenge salesman problem, and many other combinatorial optimization problem over the graph. Okay, with this, I'd like to just conclude. So essentially, what I have been talking about here is some family of deep learning model defined over graph structure. So the key kind of property of this kind of deep learning model over graph is it will learn some vector representation for each node in the graph, and this vector representation is learned by in an iterative fashion, and through some kind of message or passing operator parameterized by neural nets. This type of graph neural nets is allowing you to integrate both structure information about the graph and also some additional node information. It opens up lots of possibilities to bridge deep learning algorithms to logic reasoning, and then even computer vision problems and combinatorial optimization problem. And this graph neural net-based model can actually also connect to lots of different objective functions, such as supervised learning, generative model reinforcement learning, to solve a diverse set of problems. And in this particular presentation, I just pick a few examples to show you, the potential application of graph neural net. But there are many research. Doesn't matter whether it's in machine learning, computer vision, or natural language processing. Graph neural net has been extensively used, either in terms of innovation in the architecture of this graph neural net, or novel applications, including my group. We have done a lot in terms of using graph neural net to solve various problems. If you are interested, you can check into some of this literature and find out more about some of the application of graph neural nets. Finally, before I end the talk, I just would like to take the opportunity to introduce a bit of the bigger picture of my research, or what I'm interested in. I am a machine learning person, but I also work quite broadly from several kind of dimensions. I have been looking into, for instance, the large-scale machine learning kind of algorithms, including designing efficient optimization algorithms such as W-stochastic optimization for kernel method and distributed method for kernels. So that actually leads to one of the IPDPS best paper. And I'm also working on the representation of functions, nonlinear functions in machine learning, including kernel methods and then the deep learning. They're all representing nonlinear functions, right? It can be graph neural nets. It can actually be convolution features for the image as well. And I've also been working a lot on probabilistic graphical models. You have been seeing graph neural net applied to graph data, but actually another set of method for dealing with the graph is probabilistic graphical model. So I've been looking into such as spectral algorithm for hidden markov model, or even some kind of dynamic event data from graph as well. And optimization is also something I'm very interested in, connecting especially optimization method with sampling method. Okay. Besides that, on top of these three pillars of machine learning methodology, I am particularly interested in application arising from network graph or data with structures. Okay. And such data occur a lot in social network, in interdisciplinary problems such as computational biology, material science, and healthcare. If you're interested in either the methodology kind of direction of machine learning or application direction of machine learning, just come and talk to me. Okay, that's pretty much my talk. If there are any questions, we can go to the question and answering session.
Yeah, thank you, Professor Losong. So if you have any questions, please type them out in the Q&A section. I think there are already a couple of questions. I think the first one is, when you do this structure to vector embedding, does it destroy some semantic information? Like, how will you understand which features are significant and which are not when you're applying, let's say, a black box kind of algorithm for the prediction?
Yeah, very good question. Yeah, so in some sense, this is a common problem of deep learning. You're taking the input feature, in this particular case, a graph connectivity structure, and with additional potential edge type, node type information, and then the maybe additional node information, compress it to some kind of dense vector representation. In some sense, the benefit of this process is you learn to select useful features. The disadvantage is it loses some meaning. So people have, in the recent 2 years, looked into explainable model for graph neural net, trying to explain, the prediction of the property, for instance, for a particular node is due to maybe the presence of this neighbor with that type of node and that type of edges. So there's a set of explainable model one can actually use to try to explain the decision made by graph neural nets.
Okay, thank you. The second question is on what are the state-of-the-art methods to generate graphs and relationship within data, especially in the case of tweets?
Yeah, so generative model for graph, there's quite a lot of work being done in the past couple of years as well. So depending on the type of graph you generate, the state-of-art method is different. For instance, if you want to generate small molecules, actually people will have some model which is like a reinforcement and generated node by node and attaching the newly generated actant to the existing molecule. That can be very efficient, easily trained because the graph is small. And if you are going to distribute a network, which is very big, right? There may be many network and many nodes and then many connectivities. The efficiency is a big consideration. So in terms of scalability, one of the most recent work actually done by my student, Han Jin, now in Google Brain, is actually using hierarchical way to generating these big social network. Um, uh, if you're interested, drop me an email later on. I can refer you to the paper.
Okay, so there's one more question, like how can we use a graph, GCN, graph convolution network, I believe, in unsupervised learning?
Okay, so there are actually recently it's also a hot topic for representation learning for graphs. And there you again want to learn the parameter in this graph neural net, but you're going to learn it without any label or supervised task. In this case, actually, one thing you can do is something very similar to the natural language processing case. You can create some self-supervised task, such as mask language model. You can mask out some of the node in the graph, and after you perform a graph neural net, you ask this resulting embedding to predict the missing node or the mask node. So you can imagine you can create lots of these mask node tasks and then ask graph neural to predict it. And this is one way. And there's also self-contrastive type of way to learn the representation for GCM. Essentially, you're going to take the original graph and put up the graph. After you're passing through the graph neural net, you want the embedding to be similar. If the two graphs are original from the same graph, if they are from the different graph, they will form negative pairs. And all this idea from you know, unsupervised learning of images and natural language can be actually borrowed to perform unsupervised learning in graph as well.
So the next question is asking, can you please comment on the speed and convergence of training graph neural networks, especially in the reinforcement learning setting? So if you're given a very large graph which contains a lot of paths for a long distance, it seems it might require a lot of iterations for training procedure to converge.
Yeah, very, very good question. Indeed, it can be quite expensive to train graph neural net, large, especially large graph. And then also in this reinforcement learning, there's additional complexity of, you know, there's a long time horizon for you're taking a sequence of action to achieve the result. So in terms of the large scale graph neural net training, so actually there's already lots of work on how do you train graph neural in a stochastic fashion. It's slightly different from the image case where you have clearly defined a mini batch of images. In this case, if you have a large graph, the entire thing is connected, right? How do you create a set of small tasks in order to train this graph neural net? So you also have a mini batch, or even you have a way to, you know, decompose the network into other clusters and train it in separate machines, and then before you communicate and synchronize the parameter. In terms of the reinforcement learning setting, the additional complexity comes from the time horizon of this decision process. If the graph is large, you need to take lots of decisions in order to solve the problem. So there, indeed, you need to generate tens of thousands of examples and train many epochs to converge. I believe that the time can be reduced if you have a better, you know, reinforcement learning algorithm. We didn't design anything specific for this combinatorial optimization case, but you can imagine any advances in reinforcement learning could be borrowed to the graph case and then help you speed up the training process.
Okay, so I have a couple of questions.
Mhm.
Firstly, you talked about the embedding, right? The structure to vector embedding. So how
Right.
do you design the architecture of that neural network? Are there some best practices, or
Mhm.
is it just purely dependent on the application?
So the effectiveness of architecture will depends on the application. And what I'm showing here is just the most basic kind of architecture. So for instance, if you believe some of the neighbors are more important than the other, so you can actually put a tension mechanism in the process of aggregating neighborhood information. So it's a little bit like a tension mechanism in the transformer or other places, right? You can actually attend to different neighbors. This is one architecture choice. And another consideration is whether long range information is important or not. So if you have you believe longer range information or neighborhood with many hops away are important, when you're designing the architecture, you have to have some kind of residue type of connection, or you have a way to maybe bring the information in many iterations away to forward. Um, that will actually change the details of this message passing operator. Yeah, and if you have different type of edges or different type of nodes, that will also kind of affect the architecture. So it's indeed application dependent. So there are also many words goes behind how do you actually best design this graph neural net architecture to capture heterogeneous network and then long range information. And there are even some work recently using AutoML to try to select this architecture automatically.
Thank you. A related question is, so when you do this embedding, right, are there certain embeddings which are good for a variety of problems, or is it again purely supervision? Is there like a self-supervision kind of thing where you can come up with some pre-task which will help you give you some good embedding which can be used across a variety of different applications?
Yeah, it will be again domain specific. For instance, you can pre-train your graph neural net using a large collection of unlabeled molecules. Then that feature will be good for predicting molecular property. And if you're working with a big social network, then the pre-trained vector or useful embedding will be very different, mostly because of the type of nodes is different, the connectivity kind of pattern is going to be different. So it's very similar to the scenario where you have a pre-trained model maybe for natural images, right? And then now you want to apply to, for instance, a domain with just pathological medical images, right? So you can imagine that you might need some adaptation in order to make it work, right?
Yeah, so I can understand that there may be differences across domains, right? But let's say
Mm-hmm.
I'm dealing only with images, but different tasks across these images, like classification or segmentation and all that, right? So in that case, is there a common embedding?
Yeah. So for instance, you might, for instance, for molecule, right? There's a open molecule data set already very big. If you pre-train on this molecule, you will find it's good for a set of tasks such as no property prediction and then the entire molecule property prediction, or maybe different type of molecule. It will be useful for these different tasks.
Okay, thank you. So are there
But
any further?
there's no in natural language you might have this BERT, yeah, GPT-3, which are pre-trained. You can use in many different tasks. In the graph neural net scenario, it hasn't come to a standard like that, right? There's pre-trained gigantic the graph neural net model which everybody use, and then when you encounter molecule problem, just use that pre-train. No, it's still a very active research area at the moment for the graph pre-training.
Okay, thanks. Are there any further questions? You can either type them out or you can just unmute yourself and ask the question. Okay. I don't see any questions. Okay, thank you, Professor
All right.
Lasong, for the
Yeah.
very interesting talk.
Thank you. Yeah. Thank
And
you
thank
for
you
the
everyone
question.
for attending.
Yeah. Okay, see you then. Bye.
Thank you. Bye. Oh, sorry, this one.
Yeah.